So our third speaker is Dr. Stephen Wilson. I can still call him adjunct professor because he was at UQ for 3 years teaching, who will be speaking on the effect of nuclear energy on total system electricity costs. Stephen Wilson, my friend, is an engineer and energy economist with over 30 years of experience in energy generation, distribution, storage, and systems. He is the lead author of the report, What Would It Take, or What Would Be Required for Nuclear Energy Plants to be Operating in Australia past 2030. A handy reference, I would say, for anyone wanting to delve into the question of nuclear power and how to do it safely, cohesively, with a circumspect mindset. Stephen Wilson has worked in several major consulting and mining firms, most recently, as I mentioned, as professor as well at the University of Queensland, and is currently undertaking advisory and research work. So please make welcome Professor Stephen Wilson.
Thank you, Mark, and thank you to the ANA for having me once again. I must be saying something right. This is the third time I've stood up in this room in the last few years, and things just keep getting better and stronger. I've been saying on social media this will be the best ANA conference that I've been to, so this is wonderful. Mark mentioned, this is just for disclosure, I've got several hats. I haven't quite got 6 thinking hats yet, but I think there's 5 here, ranging from advisory work to advocacy, the research work and the collaboration with colleagues at the university I'll talk a little bit about today. And I've recently been appointed a visiting fellow at a think tank where we are establishing a program of work on energy security, and I'm also director of a startup company. At the 2019 ANA conference, I stood here and said that without nuclear power generation in the system, I think we'll find it's close to impossible to deeply decarbonise the Australian economy. That's exactly what Jeff was just talking about. That was the key point of left-right agreement in the United States on these issues, was that realisation. But having said that, I also said 4 years ago it would be a mistake to think that nuclear will just happen automatically or inevitably as a result of that. There is a lot of work to do. Now, I've been told that in the United States it's very common that you should start a talk with a joke. And I don't want people in this room to think that I'm some sort of grumpy old conservative that happens to be criticising the present government. And so I would strongly advise everyone in this room to read the memoir of Mr. Howard. And the reason I suggest that is he has a whole chapter on climate and nuclear. And it's been pointed out to me that the policy that was introduced in 2001, the Renewable Energy Act, is the only thing that he admits in that memoir was a policy mistake. So he's actually criticising himself there, and I think it's really worth understanding that and reflecting on that. So we should perhaps leave the jokes to the professionals. This is a very perceptive cartoon, very, very perceptive. And the reason why is that it's a drawing of the power cost paradox. What is the power cost paradox? That's one of the things I want to unfold in this talk. Imagine you're the minister and you're presented with these 2 numbers. Minister, wind and solar is $50 a megawatt hour levelised cost. Nuclear is $100 a megawatt hour levelised cost. How much of each should we build to get the lowest total system cost? Okay, so there's a lawyer, there's an accountant, and there's an economist, and they're in a bar and they're arguing about this. Most of the parliament's full of lawyers, as you know. The lawyer says, well, this is ridiculous. The question is completely irrelevant, it's moot, nuclear energy is illegal in Australia. The accountant says, no. The answer is obvious. I mean, clearly, with simple arithmetic, we can see that the answer is you just build a 100% wind and solar system. The economist says, no, you're both wrong. Even talking about this is ridiculous. Just let the market decide. So I want to talk about that power cost paradox a little bit. There's also a power system paradox, and there's a power market paradox. We're facing a saturation issue in the system. We need to understand what balancing is in the sub-second, from the sub-second resolution to the multi-decadal resolution. That is 12 orders of magnitude. You know, so that's the difference between $1 and $1 trillion. And that's why I've been saying since the Victorian Parliamentary Inquiry and in the UQ report that Mark referred to, that we need a plan B. We are capable of deploying nuclear energy in Australia, and our main recommendation in this study is that we need to create real options, and we need to do that starting now. So I'm going to refer to three pieces of work, or three things that I've been involved with. The first is a chapter that I was asked to write in the book that came out of the Submarine Institute conference at the Australian Strategic Policy Institute in Canberra in 2019, which was a seminal moment in the decision to change the submarine, to walk away from the diesel hack on the French design and replace it with a proper nuclear submarine. The UQ report answering the question what would be required for nuclear energy plants to be operating in Australia from the 2030s, and the thesis of Gabriel Riosico, almost doctor, hasn't quite picked up his gown and his piece of paper yet, looking at the cost of the national electricity market or the eastern system if we try to decarbonise without nuclear versus if we allow nuclear in that system. So in the kind of core thing that I did in this chapter 8 of this book, which I titled Too Cheap to Meter or Too Expensive to Matter, was I wanted to just demonstrate how silly it is to get obsessively focused on the levelised cost of energy. And so the first two columns of numbers there are straight from that book chapter. And all I did was I said, yes, I too can play this childish game. I too can give you a $330 a megawatt hour levelised cost. And then I can tweak a few little dials and I can tell you it's $65. There's a few corrections to some of the wrong gen cost assumptions in that on the left-hand side, and a few other little tweaks of the dials. So, and then the third column, what I've done is I've just made a few updates. NuScale have uprated their capacity from 60 to 77 at no increase in capital cost. Now, people are debating with me a little bit about some of the input numbers here, but the main point is an obsessive discussion about levelised cost is fundamentally ill-informed and childish. LCOE is not an investment grade metric. Nobody goes to a group of banks and finances anything on this basis. What do? They talk about building real projects, and that was the focus of the UQ report. How would you build a real project? What would be required? What would you have to do to get to that thing in the middle called financing? You've got to deploy a lot of 100% upfront equity capital, step by step, approximately times 10, times 10, times 10, with each step from scoping. We're not yet at scoping. We've done the preliminary concept study. And you can judge what you think that document's worth. The scoping study, I think we need at least $5 million. Pre-feasibility, we need $50 million. Feasibility, EIS and approvals, we probably need about $500 million to get to our first $5 billion large civilian nuclear energy plant. And so what that costs in the real world is all about project management and delivery and all those issues. So, you know, there's a lot of uncertainty on the left-hand side, and as you move towards the right-hand side, you're de-risking and reducing uncertainty. We're following the discipline of the AACE method here. At the time we did this report, NuScale was kind of in a hybrid of a class 4, class 3 estimate, and the numbers we published in 2021 are based on that. They're probably sort of somewhere between 3 and 2 now. I haven't looked at that in great detail, but they're moving forward. So the big message here is costs cannot be considered simplistically or in a vacuum. But we do have to start by thinking about the asset level of costs. What would it actually cost to build a nuclear plant in Australia? And that was what we focused on in this report. And then I'll build up through a number of other costs, perspectives on cost as we go through this talk. So when you think about that question, what would it really cost to build a nuclear plant? This is not a simple question. And so when Barry Murphy sat me down in the Regatta Hotel and asked me that question, and I said, well, Barry, that's a huge question. Actually, it's 7 questions. Turned out to be 8 questions. So there's 9 words on this slide, the context and then 8 headings, and we looked at each of those. So if you want to form a view on cost, you need to understand that under each of those headings is a whole bunch of stuff that will affect the answer you come to on cost when you are trying to deploy a real plant. Top left is about context. I'll talk a little bit more about that in a minute, but I will say that, and this links very strongly with what Jeff said, in that top left box is, you can think of the word models. There is a battle of the models. It has begun. That conversation needs to be managed in a very intelligent and civil way, which is kind of what Jeff was describing happened in the US between left and right, and the Chatham House rule and the closed doors and the light bulbs going off, let's say, in people's minds. So here's what we came to with our cost estimate in the UQ report. It's on page 35, table 5. In the financing chapter, there's the numbers so you can actually see them. This is the thing that shocked me. You know, this was peer reviewed by, I don't know, 28 people, Australia, US, UK, Europe. One of the things that really shocked me about that review process was how little challenge and pushback I got on these cost numbers. It's very interesting, despite the fact that in the debate, it's a very fraught conversation. So I'm totally open to having conversations with anyone in the world, engineers, economists, anyone, politicians, about these numbers and what they mean. So, but we can't just think of individual plants in isolation. We need to think in programmatic terms, and we need to think about a fleet. So how would the cost come down from that first plant to the nth plant? So there's the first plant in the world, which Jeff has mentioned. Our American friends are going to take the risk on for us, and we should take full advantage of that. Some of you might be familiar with the grub curve. This is the technology learning process. You know, you come with the original idea and you think it's going to be fabulously cheap, and then you start peeling the onion in the lab and you start building things on the bench, going through the development process, and you realise it's not as cheap as you first thought, and so you go up that first part of the curve as you go from TRL1 to TRL6 or something like that. And then you start to demonstrate pilots, and then you get to full-scale commercial development. So from sort of 6 to 9, 6, 7, 8, 9 is typically a scale-up process for most technologies. The smaller the technology, the less the scale-up challenge. So Gen 3 reactors are probably sort of somewhere part-way down that deployment curve. You can debate exactly where. Large reactors, obviously, you know, Gen 2s and older technologies are mature. And of course, the things that people are comparing us with, the old coal plants and gas plants and wind and solar, are already mature technologies. They've spent a number of decades with significant support getting to the top of that hill and then coming down the other side. Now, if you look at the SMR dashboard that's published by the Nuclear Energy Agency of the OECD, this is a snapshot for the NuScale plant, which was what we took as our example in the UQ study. I think they're being very conservative, actually, on the maturity. I think they're probably, you could argue they're more mature on siting and licensing, and fuel siting and licensing than would seem to be indicated here. But you know, there's multiple parameters in getting to nuclear that you've got to tick off across these headings that are shown in that radar plot. Now, the big thing I learned from appearing and giving evidence in all 3 of the parliamentary inquiries in recent years, the federal one that Ted O'Brien chaired, the New South Wales one that Taylor Martin chaired, and the Victorian one, in the upper house, was that almost nobody will stand up publicly and say, I am anti-nuclear. In the old days, and you know, in the sort of 60s, 70s through to the 80s, it was sort of like a badge of honour that you had to be anti-nuclear to be an environmentalist, etc. And the story was war or warning, you know, weapons, accidents, radiation, and nuclear waste, so-called nuclear waste. Now, it's just cost, it costs too much, and it takes too long. So this is the battlefield. This is not the battlefield that the pro-nuclear people have chosen to fight on. I mean, fighting on a cost battlefield is one where nuclear will win if you understand properly the costs. But that is where we need to engage, because that's where the opponents of nuclear have chosen to engage. And so we need to be really on top of all this cost stuff. So does nuclear cost too much? This is a slide thanks to which Dave Collins brought back from Korea at a recent international conference. He was the only Australian there flying the flag for us. The overlay with the red text and the red lines is mine. And the thing that struck me about this is that the examples that people are always quote, the anti-nuclear people are quoting the cost examples from the West, Britain, France, Finland, US. But you look in the East, not even the Far East, even the Middle East, and it's just a completely different story. So that's why I'm provocatively asking, does nuclear energy cost too much, or are Westerners stupid? You know, Chinese people are polite, but they secretly, you know, wonder whether Australians are fat, rich, lazy and stupid. And I can say it because I'm Australian, 5th generation on both sides, right? So, you know, we need to ask ourselves in the complacent West, why can't we do that? Or what would we have to do to achieve that, right? Because the countries that do not master nuclear technology in the next couple of decades will be completely left behind by 2100, climate change or no climate change. So, and it takes too long. So, you know, these big plants, they're taking sort of, you know, 2,500 to 3,000 days to build. That's kind of what it's taking. And in other places, you know, Finland and France, they've sort of taken 6,000. But once they've got that asset, that's a 60, 80, 100-year asset. You know, they'll be enjoying the benefits of that long after they've forgotten how much it cost and how long it took to build. So what is the effect on the system of the first, second, third, and the nth of a kind plant? This is something I borrowed from that submarine study with the chapter 8 on the costs of civilian energy. The solid black line is a kind of a representation of the short-run marginal cost, so the variable fuel and operating cost of different plant types as we have in Australia. You know, we've got some hydro, then we've got some very low fuel cost brown coal, then we go to Queensland and New South Wales black coal, then we get into the gas plants, combined cycle and open cycle at whatever gas price you want to assume. The dashed line is what happens when you insert zero marginal cost, short-run marginal cost wind and solar, free energy, quote unquote, and you shove that curve across to the right. The grey line is what happens when only thermal plants are generating. So when the hydro, we don't have baseload hydro in Australia. You can run hydro in the intermediate and peaking regime. There's not enough water to run it all the time. So when if the hydro is not running, then you move to the left. And so that cost curve, and if there's a drought, so there's a weather dependency sitting underneath the cost curve, which is moving that whole thing to the left and the right. The sun goes down and the wind doesn't blow and it moves to the left. Now, this is a sort of 2 decades of the operation of the national electricity market, and this is the annual average spot price and annual energy on the horizontal axis and annual average spot price on the vertical axis, and how that evolved. So the market was working beautifully for, you know, a decade and a half, and then things really started to go slightly crazy. We've gone from a black coal short-run marginal cost price formation environment to a sort of a gas constrained short-run marginal cost environment. Now these are annual average numbers. Keep that in mind as we go forward. This is Gabriel's first look at the international literature and his own residual cost analysis on going from 0 renewables to 100% renewables. This is the question, how much extra does it cost to integrate these resources into the system? And it's very clear, with the exception of one group at ANU, it's very clear that for all the people around the world is that integrating weather-dependent variable renewables into the system dramatically drives up the system costs. Now, so that was lit review and first spreadsheet analysis prior to building the model. Now, before we talk about the model, it's really, really important to know that there is no single full fidelity model of a power system anywhere in the world. It's very important to understand. If someone presents you with a model as if that is the final answer to everything, they either don't know what they're talking about or they are intentionally misleading you, right? So you've got to keep that in mind when you look at these modelling results and any others, okay? But there are plenty of useful models. Models plural, you need more than one model to understand the system. What are we trying to understand? We're trying to understand this system, which currently looks kind of like this. This is a kind of week in the life of the NEM, mostly brown and black coal, a bit of gas, some hydro, wind and solar. This is straight off opennem.org.au. New South Wales is mostly black coal and some imports from Victoria. Queensland is mostly black coal and exports south to New South Wales. Victoria is mostly brown coal and some imports and exports from South Australia, to and from South Australia and New South Wales. South Australia is a mess. It looks like that. It doesn't work on its own. It only works because it's got it's very, very small, and it's got a high voltage connection to the Victorian brown coal in the Latrobe Valley. Tasmania is mostly hydro, has no problems. These are all synchronously connected as regions operating at one frequency. Tasmania is a DC submarine link, and there's another little DC link up at the Murray River. So that's what we're trying to model. Like, what is the cost of this thing as you dial up the wind and solar and try and make the whole thing look like South Australia? So here's another zoom in on South Australia. The line at the bottom is the half-hourly spot price, or actually the 5-minute spot prices, and you can see they tend to wildly swing between peaks that go crazy upwards and negative prices. So when the sun's shining and the wind's blowing, the prices are negative. Please explain to me how you earn a rate of return on that investment. The answer is these machines are not primarily power generators. They are certificate creators. Their primary product is the issued certificates from the federal government. That is what underpins their bankability. And then they just dump their product onto the market, and you guys deal with it. Please work around me. Here is one snapshot from the thesis modelling that Gabrielle's done. This is the halfway point from decarbonising from about 600 grams a kilowatt hour to about 300. A typical week in the NEM. And you can see it's basically, nuclear is coming into the baseload as coal is retired. So we're talking about a future where part of the coal fleet at this point in time has been required. Please optimise on a long run basis and simultaneously on an hourly dispatch basis. Fully decarbonised looks like that. Now this shocked me. So let me be really clear. I did not make any adjustments to any of the results that Gabriel produced in his PhD thesis. This is all like straight out of the box results. And one of the things that surprised me is that the paper from 2015, Can Renewables and Nuclear Be Friends? Yes, up to a point. So there is a way to integrate if you've got flexible, fast rampable nuclear, which is the example that we're using. We're using our cost estimates from that UQ study plugged into this model. All the other cost estimates are from GenCost, but not the nuclear ones because we don't trust their nuclear estimates. So what does that mean cost-wise? Well, as you go from the kind of system we've got on the left to a no thermal generation decarbonised system on the right, you go through like 3 times overbuild and you end up with 6 times capacity overbuild. You're building over 200 gigawatts of capacity to serve a 35 gigawatt peak. What does that cost? Well, before you include all the costs, it's like at least $180 a megawatt hour before you account for what actually happens in a market environment. Then you got your transmission, your distribution, your control, all these other costs on top of that. And then, through distribution and down to the customer bill. Allow nuclear into the picture. It's very interesting. So we've done this with different levels of capital cost assumption on nuclear. I just focus on the zero carbon systems, right? So if you assume that nuclear is low cost, like under $5,000 a kilowatt, yeah, it builds a lot of nuclear. But this is another thing that shocked me. Even if you assume that nuclear is almost $10,000 a kilowatt, guess what? If you're trying to decarbonise the system, it still wants to build lots of nuclear. This is a really stunning result. I mean, what this shows is that the capital cost of the nuclear plants doesn't matter as much as people think. And the cost of that first-of-a-kind plant really is not as significant as people think, because the first-of-a-kind plant is so valuable to the system because it can do everything. It can give you baseload, it can give you flex, it's zero carbon. So, without nuclear, we're talking about $180 a megawatt hour plus. With nuclear, we're talking about $90, minus. Okay, that's kind of the world that we're talking about here, folks. Right, so the value to the system, including the real option value, that's what the system used to look. This is a month in the life of South Australia in the NEM in the old days when they had a coal plant. And, that is textbook, Fred Schweppe, MIT, 1988, price formation mechanism. That's what it looks like these days. I've shown in this room before that step by step, month by month, and state by state. This is not cherry-picked South Australia. I'm not cherry-picking August. This is the disease that we are dealing with. This is the high price volatility disease. You can see the level has increased significantly. You can see the energy is actually slightly less, and that's what happens in the market design we've got. And Bill Hogan at Harvard thinks this is all fine. Paul Josko at MIT and Dick Schmelency in 1983 said, I think there'll be a problem, folks. So keep in mind that a system is not the same as a market. The market needs the system. If the system's not working, everything's black and there is no market. The system needs the market. So the market needs the system, but the system doesn't need the market. So we've gone from that world, we've blown up the coal plants, and that's why I said in 2016 at the engineers conference, I asked the question: is the market dead or just resting? So this thing is unforecastable and unbankable, and don't believe me. Go and talk to the bankers. In mid-2017, we talked to all the big Asian, Australian banks, the Asian banks, the American banks, the European banks that are in Sydney and Melbourne. They all told us the same thing. Chatham House rule, but this quote captured what they all told us. No one can produce a bankable price forecast of the market today. You need a long-term power purchase agreement, or in the case of renewables, it's all banked off the certificates. So we said in the UQ report, when Mark Ho first sent me this paper, I didn't believe it. I said, Mark, no, I don't think that's true. I think, if you're flexing your nuclear up and down, it'll undermine the revenue line and it actually won't work. But we've run this for the whole system through an optimizer, and actually it's true. It does work. So keep in mind, people want to run to green hydrogen. That's completely uneconomic. We've done the research on that. Frequency stability is a massive issue. If we don't get on top of these issues, it's just going to get more and more and more expensive to keep the system stable. So, we were in a world over on the right-hand side there with, low-cost old coal plants. The alternatives are very, as you try and decarbonise without nuclear, you're moving towards the left, and up and up and up goes the cost. Wind and solar, this is the power cost paradox. People think it's there, but you integrate it into the system and you find out, it's actually up there. And then, so that's why we're interested in SMRs and nuclear energy, which we think sits in this zone down here. So what about carbon costs? I haven't talked about carbon costs. I think it's naive to just think, we just slap on a carbon price and we solve all the problems. That's a long conversation. But just a reminder that this is Australia's official national greenhouse gas emissions. All gases, all sectors, and CO2 equivalent. Okay, it's dominated by CO2 from the energy sector, as you can see, and that's the history from Kyoto, from Rio Earth Summit to Kyoto to through to Paris, and what we've signed up to. Now, implementing this will kill the electricity market. It is killing the electricity market. Okay, the electricity market is fundamentally dead. It's just for the British to see at the moment. Now, all my conservative old, right-wing nutcase friends are really mad at Morrison for signing up to net zero in Paris, right? My view is that he had no choice. There is no way he could have got the AUKUS deal with Biden and Johnson. I've tested this with some very senior retired politicians. There's no way he could have got that deal if he didn't get on the plane, go to Glasgow and pledge net zero. Okay, was that the right thing to do? Yes, I think it was. Why? Because energy security is really important, right? So we need to, when we talk about cost, we also need to be conscious of the whole big picture. Okay, so energy security considerations at the national level. This stuff's real, it's happening. People get it. They definitely get it in Washington. How do we know? We went there and talked to people. Jeff was one of them, Rita was one of them. And a lot of other people. So and James, who's here, was with us with Ted O'Brien, and that's where we went, and that's who we saw. And one of the big messages, probably message number one, was energy security is national security. Every single meeting, right near the start of the meeting, before we asked the question. Now that's a quote from the head of the US Nuclear Energy Institute. And so, little ad here for the work I'm doing on energy security. we've defined it as the power to be free and to do work. We're calling it the Canberra definition. I put that up first in Canberra. That is not from thin air. That's the overlap of the definition of energy from the dictionary and the engineering textbook, and the definition of security from the... So we've got to think about this picture holistically, and cost is going to be at the centre of the battleground. Mark, thanks. I'll hand back to you.